full screen. There we go. Okay, so I've been helping out for a few years on and off with looking at some of the things going on in cold fusion, or what we now call lattice-enabled nuclear reactions. And I'm just going to try to provide a general overview of some of the stuff I'm looking at, and kind of a background on the field. I try to, there's a lot of physics going on here, so I'll go try to explain some of the physics as we go. If you want to ask questions, go ahead, but I'll try to keep it simple to begin with. So for those of you who don't know the backstory, in 1989, there was a very famous experiment that was done by Fleshman and Pons at the University of Utah. And what they did was they took a metal cathode, like a palladium cathode, and they put it into heavy water, which is water with deuterium, deuterated water. And then they ran current through it. And what happens is that the deuterium in the water is thought, it starts to collect into the cathode. And over a period of time, you can measure the heat using a basic calorimeter, the kind of thing like you measure the heat. This is like a styrofoam cup, you can imagine. Here it's a flask. And they measure the heat. And what they found is that there was this excess heat that came out. And there's a huge amount of heat. And the claim was that this was some sort of nuclear fusion going on inside the cathode. And this was a basic experiment. It was featured many Time magazine and on the news. It was a huge thing that happened, a huge news story back then. And this is an example of what an experiment might look like, where you have two reactors like this, one with plain water and one with deuterated water. And you basically run over many hours. Here's like 600 hours, and you put regular water in, and you measure the, in this case, they're measuring the current that's coming out. And you see that you get this, which is how they measure the heat. And here you see really very little happens with regular water. And with deuterated water, at some point after about 500 hours, you start seeing this huge increase in power. And this is a classic type of experiment that people have done, and many people have tried to reproduce this. Some people have failed, other people claim they've made success. And this is sort of the story of what's going on here, what these experiments are about. Now, I know some of the people who were involved in this many years ago, because I was working as a quantum chemist. I was a postdoc at the University of Florida for a while in the quantum theory project, and I had worked with a fellow who was an expert in muon catalyzed fusion. And so at the time, there was actually another fellow named Jones, who at the same time, who was at Brigham Young. And at the same time, he was saying that he could also observe cold nuclear fusion in condensed matter. And again, here he has current dispatched through palladium or titanium electrodes immersed in an electrolyte of deuterated water and various metal salts. And they see a small but significant flux of neutrons. And they actually claimed to detect neutrons. And so you can read a little bit about the history of this, but this was a huge controversy because Jones was a specialist in something called muon catalyzed fusion. And he had actually written an article in Scientific American a couple of years ago about something called cold nuclear fusion, which is muon, and they had claimed that you could observe nuclear fusion inside the Earth's core. And so this was actually well known. When I started working on this project with Carl, I talked to my old advisor at Chicago. So yeah, we knew about the stuff they knew about Jones's work. And so at the time, this was sort of scientifically accepted that this is a possibility. But what happened is there was a bunch of controversy around this, and there was a bunch of controversy around this, and Jones and Pons and Fleshman sort of had a falling out. You can read a bit about the history of this, but basically, the long and short of it is Pons and Fleshman went to the press. They submitted a paper Jones and Pons and Fleshman were supposed to submit their papers at the exact same time on the same day, and the day before, Pons and Fleshman submitted the paper without them and went to the press and made the announcement. And this caused a huge controversy. And Jones his paper was actually published. They published his paper in Nature, and Pons and Fleshman was not. Now, a lot of this, a lot of the theory around this is because people want to know who owns the patent, right? This is a huge advance. Richard's here, on the call, our expert, a world expert in patents. And I thought you might want to know that there's actually some history toward this. So apparently in 1927 and 32, there was a guy named Tannenberg in Sweden, and he had used an electrical cell to try to claim that he had seen fusion. He was able to produce helium from hydrogen. This is in 1927. Nobody believed him. Nobody believed it was possible, and he couldn't get a patent on it. Then, when deuterium was discovered, he repeated the experiment, and apparently, he could not get. He was denied a patent. And apparently, my understanding of the history is that when BYU discovered this, it showed that Utah didn't have priority over the discovery, and there was some controversy over the patent. So, and even today, there's still a huge controversy over the patent. I'm seeing a chat. I can't read my chats while I'm doing. I don't know if you guys just chime in if you want to mention something. Well, so sorry. So a little bit of the physics here. I go back. I screwed up. Well, give me a second. I don't know how to go back in this application. So, well, go ahead. I can't hear you. Go ahead. Sorry, give me a sec. Sorry, guys, give me a second here. I'm not an expert in.
No, your audio's good.
Yeah, I'm just having some trouble with the PowerPoint. I actually don't know how to go backwards in this, so just give me a second here. I'm going to stop the screen share and try to fix this. So just give me a second here.
Sorry about the chat thing. Somebody was asking if it was being recorded, so that's all.
Oh, okay. All right, let me go back to the screen share. Go back to where I was.
Can you hear me? Let's see.
Yes, Carl, I can hear you.
I was just saying that it's a real problem that the needs of people who need to patent stuff and try to make it go with a business or getting the technology out there to the public are the opposite of the needs of science researchers and academia. So our expectations of what good behavior is are the opposite. If you want to get something out to the public or you want to be a scientific researcher. And so it's a real big problem. It's not limited to this situation.
Yeah, no, I think this is the classic. This is the one they teach in school, like what not to do, because it's a huge, but it's an amazing story. Even for me, it's amazing to see this, to come back to this, because I had worked with some of these guys a long time ago. Let me give you a little bit of the, and it's a huge problem, right? I mean, having universities dealing with patents is just, I think Stanford has it figured out, and a lot of these other places are just, they haven't figured it out. So here's kind of what's going on from the physics. You imagine you have a nucleus, and in the nucleus of your atom, you have protons, which are positively charged, neutrons, which have no charge, and you have electrons sort of on the outside, which are negatively charged. And when we talk about heavy water, we're talking about something like a hydrogen atom, which has an extra neutron in it, but the same number of protons. This is an example of a helium atom, 2 protons and 2 neutrons. So here's an example of hydrogen. Hydrogen with an extra neutron is called deuterium, and hydrogen with 2 extra neutrons is called tritium. And the deuterium and tritium are the forms of hydrogen which are more likely to undergo fusion. Hydrogen can also undergo fusion, but deuterium is just easier. And the reason for this is because of the strong force. What happens is the protons and neutrons attract each other. So when you have more of them, they're more likely to attract each other. They stick together. They like to stick together. So there's more of them, there's more stickiness. So what we realized that heavy water, the thought was that heavy water, if you stick it in this palladium catalyst, might actually undergo fusion. Now, this is the actual proposal, which was put forth in 1934 when deuterium was discovered. So deuterium, you take 2 deuterium atoms and you combine them, you can get a proton plus tritium, and that's the top reaction here. Proton plus tritium, 1 proton. Tritium is, or you can get, actually this, I'm sure I'm showing this correctly, or you can get a neutron plus helium-3, which is a helium which is missing 1 neutron. So you can get tritium or you can get helium-3. And these are the reactants that arise when you do any kind of nuclear fusion. So if deuterium-deuterium fusion is happening in the metal lattice, you would expect to be able, it's with some difficulty, you would expect to be able to measure tritium and or helium, because these reactions are about 50-50, at least in the gas phase. So the idea was that metals like palladium can soak up deuterium atoms. So if you were to look inside the lattice of a palladium crystal, you would find the palladium sort of sits at these points here on the cube, and the deuterium and hydrogen atoms, hydrogen can sneak in and gets inside what are called these interstitial points, and it just sort of soaks it up. So the deuterium can really soak up a huge amount. And this has been known since the 1800s. So it soaks up all this deuterium, hydrodeuterium. And so the idea is if you can get a lot of very high density deuterium into the metal at very, very high density, and not too high. And if you can somehow get it either at the surface or inside vacancies or cracks, there are always imperfections in these metals. And if you can go inside into like a vacancy or a crack, that's an opportunity for fusion to occur. And that's what a lot of people think is going on. Now, there was a problem when this first came out. There was this problem because basically Pons and Fleshman were electrochemists, and they did this experiment. Said, well, where are the neutrons? Where are the neutrons? Well, neutrons were measured by Jones, so that was sort of, there were some people measuring, but neutrons are very hard to measure. You would expect to see neutrons. You might expect to see transmuted elements in a nuclear reaction. You produce neutrons. Other atoms absorb the neutrons, and they transmute. Or you might expect to see energetic particles, alpha, beta, gamma particles. So the problem is, if this is nuclear, where are the nuclear products? You should be observing them. And when this, of course, this was first done, it was an initial experiment done by some chemists, and they were not necessarily looking for this. So just an example, what I mean by alpha, beta, gamma. Okay, so this is a old notation, but basically an alpha particle is like a helium atom, and it can be blocked by paper. So you can imagine it's very, very hard to measure alpha particles because they won't escape the container. So it's very hard to measure them. Beta particles are electrons that are ejected in nuclear reaction. They'll pass through paper, but they get blocked by simple metals like aluminum. So again, very, very hard to measure beta particles. Gamma rays, on the other hand, are very specific X-rays. They can pass through just about everything except lead. And one of the things you might want to try to do if you're running a nuclear reaction is to look for some sort of characteristic gamma ray. And that's a very common type of experiment which is done. And over time, there have been many, many experiments, and people have claimed to be able to detect one or more of these types of energetic particles from these reactions. So, over the past 25 years, I guess, almost over 20 years, that slowly people have been able to detect these things, and that's why we believe this is happening. Now, there's also a deep theoretical problem with this, and this is one of the big problems people have, even if they claim the measurements. The physicists don't understand how this could possibly happen. And the reason is that if you take two deuterium atoms and you try to squeeze them together, they repel it. The electrons on the outside, this electron on the outside of the atom repels each other. And if I were to like measure the distance between the atoms, this is, at this distance, you have a nice molecule. But as you squeeze the atoms together, the energy goes up, and it just explodes. So there's no way. There's a guy named Koonin and Naumburg in particular argued this, that there's no way this could happen. So Koonin is one of the guys who's been denying this for a long time. So how could this happen? Well, remember I told you there was another guy named Jones who did experiments at the same time. Well, he was an expert in something called muon catalyzed fusion. Muon catalyzed fusion is well known. It was discovered by Alvarez in 1957. And there was a very famous calculation done by a guy named David Jackson. And anyone who studied physics had to study Jackson's book on electromagnetics, which is considered the hardest book. It's the hardest course in all of electroengineering and physics is to go through Jackson. It's a very, very hard book. But Jackson did a very famous calculation on trying to compute whether muon catalyzed fusion could be used as a power source. He concluded that it could not, but it still is a real thing. And what happens is a muon is a heavy electron. It's one of these funny particles that exists. It's a heavy form of an electron. And when a muon circles a hydrogen atom, because it's heavier, it circles it, its orbit is much smaller. And because its orbit is smaller, it pulls the hydrogen atoms together. And because they're pulled together, almost by a factor of 200, they're much more likely to fuse. So this is an example of where the electron, this is an example of a type of electron screening enhanced fusion. By screening, we mean that somehow the electron, the potential between these electrons is not as repulsive as we thought it would be. In this case, when there's a muon, it's because it's heavier. So this is a very common calculation. And you'll see as we go through the talk, there are a number of people who have tried to repeat Jackson's calculation in various forms to come up with theories. And this Jackson's called a WKB calculation. So this is a lot of what people are doing, but it dates back, even the work by Forsley that we are very familiar with, dates back to the original work by Jackson. So what's the point of muon catalyzed fusion? Well, recall that E equals mc squared. Energy and mass are the same thing. So if you put electrons into a metal, they interact with each other. Electrons interact, they can bounce off each other in this collective motion, and they can interact with the vibrations of the lattice. And so so they can pick up energy. And so if electrons in a metal lattice have an effective mass. So the point is that a heavy electron is like a muon. A muon is an actual particle with a heavier mass. But if you put electrons in a metal, they also have effective masses. And the thought was that this sort of effective mass would make the electron heavier. Because it's heavier, it would reside closer. Remember before when we went back, it lets the hydrogen atoms get closer together because it orbits them more closely. And this could enhance fusion. And so there was a fellow named Jones and Monkhorst, who I know Monkhorst personally quite well when I was a young scientist. He had proposed that what we were seeing was a type of heavy electron catalyzed fusion. And so this idea has been around for a very, very long time. And this was the original idea. In fact, Jones did his experiments because they were trying to induce muon catalyzed fusion in a material. So this was the thinking starting point. Now, I want to talk about who these characters are because it's kind of interesting. Koonin is a climate change denier. This is what he does. He's a professional skeptic. He worked for the Trump administration. He wrote an article. Here's one in 2014, Climate Science is Not Settled. He's a well-known climate change denier. He's also not an expert in nuclear physics. He's an astrophysicist. Monkhorst, on the other hand, is a world expert in fusion. He co-founded Tri-Alpha Energy, which is probably the best well-funded alternative fusion company. I think they have 500 million in funding. They're collaborating with Google. He was also an expert in muon catalyzed fusion, and he's also a world expert in ab initio theory of electron screening, which is stuff that I studied. So, I mean, you have on the one hand someone who's a climate change denier claiming this stuff can never happen. And on the other hand, you have someone who is a world expert in fusion who founded a fusion company who said, yeah, maybe this is possible. So, when I started looking at this again, I go, I remember Monkhorst talking about this, and people used to tease him about it, they worked on muon catalyzed fusion, but this was always what people thought was going on. So let's take a look at some of the stuff that Larry's been doing at Larry Forsley at NASA. So here's an example of his experiments. He's done experiments where he's taken a metal called erbium. Erbium also sucks up deuterium, and he's soaked up deuterium into it. So there's a deuterated metal, and then he hit it with a 2.9 mega electron beam. And this beam excited the deuterium atoms and caused the deuterium atoms to break apart. And notice that this is very, very dense. It's much denser than what you might see in typical fusion, like a tokamak plasma. It's a very, very dense system. And by hitting it with this beam, he was able to show that you could actually see a fusion in the material. Because if you break the neutrons apart, if you break deuterated particles apart, they're going to slam back into each other and they're going to fuse. That's basic physics. But the question is how much? And it turns out they fuse 100 times more than you would expect if it were just happening in a plasma or a gas phase. And this is the key thing. And this work builds on work that we've known for a long time, coming out of a guy named Kasagi, who's done very similar work for 20 years. But Larry's work is the first one really to get published in an American physics journal with the type of very deep scrutiny that they insist on. And it's a much more sophisticated experiment than what other people have done. Now, there are two types of reactions that are going on. One is a type of screened fusion reaction where the deuterium atoms are sort of slamming into each other and producing neutron and producing, say, helium, which we talked about. The other is something called a screen Oppenheimer-Phillips reaction. What happens is you have part of the erbium itself can absorb a neutron and turn into something else. So it can transmute. And they claim to see evidence of both of, they think, what are one or more, both of these kinds of reactions, which again is really, we've suspected this for a long time, but in the physics community, I mean, this is groundbreaking. Nobody really, that this is happening, and it's happening at an enhanced rate is really a fundamental breakthrough. So what exactly did Larry do? What has Larry said that's different than that was said back in the old days by Jones and Monkhorst and other people and even Jackson? Well, his argument is that Remember, he's going to do another one of these WKB calculations, just like Jackson did, just like Kuhn and Monk, same calculation, same technique. But what he says is that the screening is angle dependent. So what they do is they think, let's treat this like, instead of like a muon circling an atom, let's treat it like we're doing a beam experiment. And what happens is, if you shine a laser onto it, like he did, like you shine a beam onto something, here's the material, there's an angle at which particles scatter off. This will produce neutrons, and the neutrons scatter off at a certain angle. And this angle is actually the phenomenon he claims, which is called electron screening. He says there's a screening effect, and I'll explain what that is shortly. There's a screening effect which is angle dependent. And it's this angle dependence which got people to think about, there might actually be something here. That's very clever. No one ever suggested before that there would be an angle dependence in the screening. And by the way, this is like stuff you might see in, I actually look, I was in the last chapter of my freshman quantum mechanics book. As usually, when you're a C, you don't get to ever get to the last chapter. But this is a very, very, very bread and butter type of physics. And again, this is the first physics paper accepted in the US describing this. So I want to talk, what is this screening thing that he talks about? So I want to talk a little about what that is. When we talk about electrons interacting with each other, they interact with each other by something called a Coulomb force, meaning that there's sort of, as you push the atoms together, there's a force. Here it's upside down. This plot is upside down. It's just, is what we saw before. But what happens is, as you push them together, the force gets more and more and more negative. And because it gets larger and larger in the negative direction, it says these atoms are going to repel each other. So you can't squeeze atoms together so closely because of the Coulomb force. But if you put atoms into an electrolyte or into a metal, the Coulomb force changes. And there's a fellow named Yukawa who worked this out. But basically what happens is the force changes by looking at this red line. It looks like this green line. So as you squeeze the particles together, the force kicks in at a much, much, much smaller distance. So the force really kicks in very small here. So you can, in a metal or an electrolyte, you can squeeze atoms together much closer than you could in the gas phase. And this is a very well-known phenomenon. It's called, and what it does is, this is what he means by screening. This is the classical. Now, in quantum mechanics, there's also a type of screening. And this is actually, these pictures, I thought you might enjoy them. They're literally from a book, which we read in graduate, a very famous book everybody reads by Maddock, which is talking about how you describe screening quantum mechanically. And you can imagine that you have a horse, and the horse is sort of running, and the horse is running by itself, and it's just a horse. But if the horse is running in the dirt, then the dirt spills up into the horse, and you don't actually see the horse. All you see is the horse covered in this sort of dust cloud that follows it. So we call it a quasi-horse. So the exact same thing happens in a material. If you have a particle in the gas phase, it's just a normal particle. But when you put a particle into a metal, it acts like a quasi-particle. So there's a collective action. And this is literally right out of the book. This is how we think about it. So an example would be, I put a charge. When I put a positive charge inside a metal, like a liquid, the negative charges circle around it. They get closer. And so they screen it. And this idea that positive charges don't like to be by themselves. So this is a collective effect. So it's sort of like they call it a clothing. So when the particle is by itself, you say it's bare. And when the particle is in the metal, there's clothing around it, or a cloud, and we say that the particle is dressed. So it's sort of strange language that you use. So you might see that you say screening, you might say the particle is dressed, or it's clothed, or it's been renormalized. So there are all these different terms that exist for what is essentially the same effect, that there are these collective effects that exist. Here's another example. You think about how electrons move. If you have a current moving through a metal, well, the electron doesn't move by itself. As the electron moves through the metal, there's this cloud. It's dressed by the metal, and it moves around. So they're quasi-electrons. And you can think of this as things like collective electron oscillations. As this electron is moving, it can feel this electron moving. Because, dipoles, right? It's the same reason that radar systems work. Dipoles resonate with each other. So when this thing moves, it sees this thing's move, and they interact with each other. So one way we describe this is sort of like when you try to write down the equation for this, they actually call this like a drunken man. So you imagine here's the electron, and it's sort of wandering around inside the metal, and it bumps into another electron, or it bumps into the lattice, and it bumps into the lattice again. And we think about it sort of like a drunk wandering around. It doesn't really walk straight. It just sort of bounces around, bouncing off other particles, bouncing off the lattice. And we call this the collective oscillation. And typically this is described by a little picture. And so the electron comes up, it bounces off something else, and it moves over here. So as two electrons are moving, they sort of interact with each other. And this diagram is called an RPA, a random phase approximation, which is literally described by this little picture. So when Larry is talking about screening, he's talking about that classical effect. Now, if you were to write down screening, this, by the way, this is from one of my own papers on the field. I did my PhD in this stuff. So if you were to write down screening, you would say, well, there's this, you get these little pictures, which are called Feynman diagrams. And you get, well, there's a Coulomb interaction. And then here's this classical interaction. But then there are all these other things. There's an infinite number of these interactions. And when you talk about screening, you're only talking about one type of interaction. And there are lots and lots of other types of interactions that are quantum mechanical. So there's all sorts of stuff going on. And why is this important? When we think about fusion, fusion is a short range effect, right? You have two atoms, they come together, they're close to each other. And so you would expect that that what causes fusion would be a short range effect. But screening is long range. So there's this question as to how could something like screening actually cause fusion? And this is probably the biggest challenge to this theory, is that physicists will ask this question. Well, these are short range effects. Screening is a long range effect, fusion is short range. And of course the answer is, yeah, there's all sorts of other stuff going on, but it's just way too complicated to treat. And that's why we only talk about the screening term. Everybody talks about screening because it's the easiest thing to treat mathematically. So there are lots of other theories. Okay, so there's a whole bunch of other theories other than screening. And the thing about the different theories of cold fusion or LENR is that they're not necessarily distinct from each other. So all of these theories may be correct at the same time, because remember, there are all these different things happening, and there are different kinds of things going on. So for example, one of the people we work with is Peter Hagelstein at MIT. And he has this idea that there's electron nuclear coupling. And so he has, basically as the helium becomes excited, the palladium will get excited and the deuterium becomes unexcited. So this is where the energy goes. The palladium gets excited, it transfers energy to the deuterium can suck it up. So there are a number of these sort of cross interactions that occur. But what is he doing? He takes something called the Dirac equation, which I'll talk about in the next talk. But this is an equation made by a guy named Dirac. And that's the relativistic quantum mechanics. And he reduces it to the Schrodinger equation, which is the classical quantum mechanics. And he says, well, what's happening is that as the nuclei move around, there's some motion. And nobody ever counted for this because they were just doing beam experiments and high energy physics. And nobody cared that nuclei were moving because, you're not in a metal. So you don't have all various nuclei moving around and bouncing around. So this was first noticed by Bright in 1937, but everybody ignores it when you study physics because it doesn't come up in any of our experiments. There's another theory, which is kind of interesting. It's called a low orbit electron, or a highly relativistic deep electron. This used to be, some people call these hydrinos. Same idea, that you go from the Dirac equation to the Schrodinger equation. You go from relativistic quantum mechanics to regular quantum mechanics, but you assume that the nucleus has a finite size. So remember that there was this theory, there's the Coulomb interaction, and I said that as you push particles together, as they get closer and closer, they repel each other more and more. But it turns out you have to assume that the nucleus is finite, is a point charge. If you assume the nucleus is finite, which of course it is, and you apply WKB again, you end up with this Coulomb interaction, which is attractive. So it actually suggests that the electron could actually act like a muon due to relativistic effects. So this is actually, I discussed this a little bit in our paper with Robert, but in a very different way. I call it a quasi-bound state. This is kind of a crude theory, but it's a curious approximation because again, when you do physics, you make lots of approximations, and the key is knowing which ones to make. And so if you assume that the nucleus is a point charge versus finite, you get different results, and that's very curious. There's another theory, which is put forth by our friend Robert Godis at Brillouin, but it's also been pointed out by Whittam Larson, also been pointed out by Mitchell Schwartz, also pointed out by Mark Parkhomov, that instead of nuclear fusion, you imagine you have a proton, a hydrogen atom in a box, and the lattice is squeezing it. And what happens is the lattice is, imagine this being like the palladium atoms or other protons, it squeezes the electron in, and the box squeezes the electron onto the proton and electron combine, they form a neutron and neutrino. Boom. And this is mediated by the weak interactions, different than fusion. It's another kind of nuclear reaction. Okay, so this is a suggestion many people have made. Very difficult to prove. This is also another form of going from Dirac to Schrodinger. So I discussed this in our paper with Robert. If you go from Dirac to Schrodinger, but in this case, you say, I want to go from Dirac to Schrodinger, but I'm going to assume I have a box. And in this case, a very, very high intensity laser. If you have a very high intensity laser, you can again derive an equation for the effective electron mass. So in other words, you put a particle in a box and you squeeze it, it picks up mass. And this will enhance the electron capture. And here are some of the equations, but basically, the idea is that once again, we see many of these theories look the same. You start with the Dirac equation, you make some approximation, like you apply a laser, you assume the nucleus is finite, and you end up with some classical equation, and you end up with a theory. So this is a good example of, again, I went back in the literature and tried to figure out where did this idea come from? You know, where did Whittam Larson get it? And I thought, this was actually, this was suggested by some Japanese researchers who were doing actual particle physics. So the idea that a laser can increase the electron capture rate is actually in the literature, and it predates any of the work on cold fusion. So there are actually physicists who have thought about this quite a bit. And basically the laser acts like a box and it confines the electron. So this is, I'll leave it here as my favorite slide. So this is sort of my general overview of LENR, talking about both we talked about some of the early experiments, some of the motivations, and sort of my take on where the theory is right now. And I'll open up for questions.
Cool. Thank you very much.
You got it.
Yeah, I think, Mike, you're hosting it today, right?
Yeah, sure.
So,
Unfortunately, this is very, very way over my head. I'm so if there's like an explain like I'm 5 for each of these different theories, then that would be convenient.
If there's a what for each theory?
Explain like I am 5 years old.
Well, I mean, basically, I want you to think about the idea that when you get the idea that you have electrons in a metal, right? Like metals have electrons in them, and the electron is moving around. And so you have this sort of picture where there are electrons and there are deuterated, there's deuterons inside here, these little hydrogen particles. And what's happening is the hydrogen particles want to come together to fuse, but the Coulomb interaction prevents this. So if we could somehow get some sort of electron, let's see if I can find the picture. Here we go. If we could somehow get an electron to somehow get inside between these two hydrogen atoms and hang out here longer than you expect, then the hydrogens have a bigger chance of fusing. That's basically what's going on. Imagine these things repel each other. There are electrons in here. If for some reason the electrons would spend more time between these atoms or around the atoms than you normally would expect, then you can increase the chance of fusion. And okay. That's essentially, that's the whole idea.
Hey, Charles, I've got a question.
Sure.
Could you kind of describe how the thinking and reasoning style of plasma physicists and chemists and engineers are different, and what constitutes proof of something in those 3 realms, and why they don't see eye to eye?
Sure. Look, when you think about, okay, so, high energy physics is a bunch of people with beams, and what they're doing is, here's Larry's experiment, right? They take a laser, or they take some other or beam of some beam, and they slam it into something. And what they do is they look at the angle of things shooting off. So you can imagine that you're trying to discover what somebody's room looks like in their house, and you can't really look inside. So what you do is you take a bunch of tennis balls and you throw tennis balls into the room, and they bounce out, and you look at the angle at which they bounce out. And from looking at the angle at which they bounce out, you try to figure out what's on the inside. That's basically what high energy physics is. And they're looking at things which are in the gas phase. So they're looking at things which are in the gas phase at very, very high temperatures. And if you ask, and so if you look at something like a metal, again, you have this idea that they're always here, right? They have the real horse, and the real horse is running, or like a particle, like the tennis ball. And when you look at like a condensed matter system, which is like a metal or a liquid, there's all sorts of other stuff going on, because the horse is running, you see the dust, you may not even see the horse. So they ignore all this because they're only concerned about looking at things. They're only concerned about the internal parts. They don't think about how things collectively interact with each other. And I think that's a lot of the confusion here, is that they don't understand how complicated things are. So you go back when I was talking about, you have these very complicated equations and all these diagrams. They'll look at like one simple little part and base everything on that and ignore all the complexity, because they just don't know how to deal with it. And they don't really do complicated calculations. So they make very simplistic models. And when you look at things in liquids, or you look at metals, it's much, much more complicated. There's all sorts of things going on. The drunk is, he's walking around, he's bumping into things, all sorts of things are happening. And they don't ever think about problems in that way. It's not their domain. Does that help?
Yeah, that's very helpful.
I mean,
But I was also thinking
Go
about
ahead.
the instrumentation that people are given to trust, because in plasma physics, the signals that you can believe in, like gamma rays, are really unambiguous and clear. But those chemists were asking them to look at information that came from one beaker being hotter than another beaker. And I don't think that physicists are very used to measuring heat.
Well, I mean, I think if you look at, the reason I wanted to talk about the difference between, I can find him. Where is he? Kuhnen and Munkhorst. I mean, Kuhnen's not a chemist. He's an astrophysicist. So he does, they look up into the sky, they have telescopes, they look at things, and they run calculations on their computer. But they don't really look at real things. I mean, they're not doing experiments in a laboratory, so they're not actually doing measurements of anything. They never do any real measurements other than a telescope. I mean, they're astrophysicists. Maybe they'll look at spectroscopy. They look at lines, X-ray lines coming from the sky. Now you look at someone like Munkhorst. I mean, he's a theoretical chemist, so he does calculations on materials. So he understood, even if you read his papers, yes, heavy electrons are very common. That's a common thing. They don't study. I mean, you look at something like superconductivity is a good example. At the time that these experiments came out, high temperature superconductivity was discovered. I think it was like 3 or 4 years earlier. Now, superconductivity is a real phenomenon, but it happens at ultra low temperatures, like, near absolute zero. So and you can describe this using some simple theoretical physics. But you think about high temperature superconductivity, it's been 30 years since the discovery of high temperature superconductors, which are literally metals at almost room temperature that superconduct. Nobody knows, what does it mean to say why something superconducts? Well, you might say, oh, I want to have a material and I want to do a calculation on that material, and I want you to tell me, will it superconduct or will it not? They're nowhere close to being able to do anything like that. Theoretical physicists don't do things like that. They don't do calculations. They're not, that's like an engineering solution, right? Here's the material. This one superconducts, this one, tell me which one's going to superconduct. They don't have a clue how to do that. So I think it's the same, and it's because it's such a complicated calculation that they don't think that way. So it even for them, they don't know what to say about it. You know, they have, sort of, and when this stuff first came out, this is why I talk about muon catalyzed fusion, because muon catalyzed fusion is a real thing, but it happens in the gas phase. And the thought was, well, just like superconductivity is real and we can make it happen in a material, muon catalyzed fusion is real. Maybe we can make that happen in a material. And maybe there's something special about the material which will enhance the ability of this to happen. Well, the plasma physics, they don't have the machinery to deal with this. This is very, very complicated. It's a very complicated problem. So I think that it's and that, when this first came out, that was the thinking. But no, they're not. It's definitely, they don't do the kinds of experiments that chemists do. They're not going to be doing. They certainly don't do calorimetry, for example. They don't do this, right? They don't do this kind of stuff. Wait, where is it? They don't do this kind of. This is a very complicated type of experiment. And it requires a lot of expertise to make a device like this work. It really is. You have to do a lot of work to calibrate it and make it work. And they just don't do stuff like this.
Well, you have to be a chemical engineer or a mechanical engineer to understand that. And physicists don't have that training.
No, I mean, I can't do calorimetry. I remember when I was I was a TA in chemistry, and I screwed up the calorimetry experiment. You have to work in a calorimetry laboratory as a PhD, and you have to build these devices. And people who get a PhD in calorimetry, they'll build their own calorimeters, and they have to know, what works and what doesn't. It's a very complicated device.
Yeah. We funded one at University of Michigan that's in this neat padded underground room with special walls and really careful temperature control. And then it's built out of these great materials that insulate really well. And so that's the high end of the calorimeter. But
absolutely, it's very complicated. Another example we talked about, look, you have a reaction occurring in a metal. So it's in this device, which looks like this. So there's, you have to measure something out here. Somebody asked me the other day, why don't you measure helium? That's very hard. The helium, it's really hard to measure helium. I mean, it leaks out and goes. How do you trap it? It's just not a simple thing to do to measure helium. It's in the atmosphere already. These experiments are very hard, and they're also very, very expensive. These kinds of experiments are very expensive. So I think that if you ask, I want to look at these kinds of particles that are being emitted, they're blocked by the device. So for example, we talk a lot about physics reactors, like light water reactors, right? And what happens in a light water reactor is that, you have, or in particular, heavy water reactors. Why do people build heavy water reactors? They build heavy water reactors because they want the deuterium to soak up some of the neutrons. That's why you use deuterium in the reactor. That's why you have heavy water reactors. The deuterium is there for a reason. If you don't need deuterium, you have a light water reactor. Well, what happens in something like one of these metals where Larry's experiment is going on, and a neutron gets emitted, well, it bounces off all the other deuterium atoms. So you don't see it because it slows it down. It acts like a moderator. So part of the problem, people claim they don't see neutrons. Well, no, because it would just be like looking at a heavy water reactor. Of course you don't see neutrons. They're being absorbed by the material. And I think that this is where people don't explain it this way, but that's clearly what's going on. That's the whole point of having a dense system. So I think that, these are not, these are things which have been miscommunicated to the physics community for a long time. But I also think these experiments are just very, very hard to do. Doing even like with what Larry's doing, which is this neutron. He has this neutron detector here. Well, I mean, you have to be a specialist in neutron detection. You have to have people who are really specialist in this, it's very, and you're only seeing, it's very hard to see it. So here in these experiments he's done, you're looking for neutrons in a background radiation. You're pouring, so these are just very difficult and expensive experiments, and it requires specialists to do it. And I think what happened is that early on, people tried to reproduce the original Pons and Fleshman experiment. They couldn't get it to work. And they're like, well, this is just too expensive. We don't want to spend any money on this because we can't publish anything. It would take us 20 years to figure this out.
Well, Pons and Fleshman spent like over $100,000 of their own personal money because they didn't want to ask the university or any NSF types for help because they wouldn't get it.
Yeah, that's nothing for a good experimental lab is funded like a Series A startup. I mean, you run an experimental lab at a university, you have, I don't know what your labs are like, Frank, but I mean, these are multi-million-dollar operations. I mean, there's millions of dollars that goes into set up an experimental lab just at a university, just to do, one simple experiment.
Right.
Yeah, an instrument could be $500,000. Like a mass spec is $500,000.
These are hard. Yeah, and it takes years. I mean, it might take. A typical experimental physicist might take 7 years to get their PhD. That would not be uncommon. It just takes. You're in the lab all the time. It's very expensive. So it's and I did it. When I was first thinking about this, I talked to some guys from Caltech about doing neutron
You can
detection.
be outside. That's okay.
So just doing like this neutron detection experiment, I had looked into, I was curious to see what it would cost to hire someone to do this. $2 million to do a neutron detection experiment properly. And that would just, no one would, if you wouldn't. So these guys are trying to do experiments on the cheap. And, you can do that, but people are going to be less likely to believe it, and it's much harder to replicate.
Yeah, I think our friends over in Berkeley, Brillo and Energy, they've spent somewhere around 17 million in the last 7 or 8 years.
That'd be
ramping up gradually, but and they have, a series of experiments and different ways of doing calorimetry, but they're not done yet.
No, I think that would be a normal cost even for running a university laboratory. To spend $17 million over 7 years, that would be totally within the budget of a normal lab. That's not even that would be totally with what you would expect. So imagine how much money you have to be pour in to do this. I think that the other thing, of course, is that you're doing experiments. Think about you have to get, you go back to the original experiment, you have to get the deuterium into this metal, palladium. So you have to pick the palladium. Where do you get it? Someone has to manufacture it for you. You have to control the manufacturer. So it could be anything. And you have to somehow get the deuterium into the palladium in the right way. So that's a very complicated experiment because you don't really know what it takes to do that. So this kind of thing it's very hard to control the, it's very hard to control the experimental parameters and to make it reproducible. And I think with superconductivity, it was a little easier because they were just looking at a very specific material which you could manufacture, and you weren't trying to basically get deuterium into the material and get it into the cracks and get it to load. It's a very complicated thing to do. It's a very complicated thing to do to make this. Getting the deuterium into the palladium in the way you want it to get it, in the way you want it, because you don't really know. It's very, very complicated, very expensive. Yeah. And I think one thing I've learned from studying and looking at some of all the different experiments that were done is how complicated it has been to figure out what works and what doesn't.
Yeah. Well, I have one theory too, and that is, physics is basically a game of math nerds, and given a choice, they don't do any experiments at all. They just make up beautiful theories and grade each other the way, Fashion and Cosmopolitan magazine is graded. Who's in style this season? And
I don't know if
no testability. But there's some great books on that, like Not Even Wrong by Smolin.
Well, that's a very famous statement by Wigner, that you're not even wrong. You invent that's from physics itself. You invented a theory that's not testable. So you're not even you make statements that are not even wrong. Look,
And mathematicians are encouraged to build castles in the sky that have no connection to the universe that we live in. But if you call yourself a physicist, you really should have some interest in our universe, in my opinion. But that's not true for a lot of them these days.
Well, it's hard. Look, we did these calculations where I have this on the screen. You see, I have this effective potential we compute for a material. I had a piece of Fortran code. I had 300 of these diagrams. I had to write a functional compiler in Lisp to compile the code from Fortran to get it to run on the Cray. I had to write a compiler just to compile all the diagrams. That was not an easy thing to do, we had, this was, and to run this thing, I think when I was in grad school, I had 10% of the supercomputing time at NCSA just to run a single calculation on a single molecule. So the actual theory to do these calculations, to do them properly, is very, very complicated. When you're dealing with condensed matter systems, and it's with what Larry's trying to do with his density functional theory. I mean, this is very complicated stuff. It's not at all easy to do a proper calculation. My advisor used to say, well, I can prove anything with Feynman diagrams. Anything you want me to prove, I can prove. I can just write down, I keep this diagram, I throw that diagram away. Now I've proven what I want to prove.
The problem with that is that not everything is true, because if you can prove everything, then you can prove a lot of untrue things. Physics is pretty much limited to two-body problems, two particles. And if it's a three-body problem, they say, well, we can't do that. Chemists deal with millions
you have to do a simulation. It's very hard. If you look at the stuff that you look at the different kind of equations, what I wanted to point out was that all of these theories look very similar. I go from Dirac to Schrodinger and I make some approximation. This is what Hagelstein does. It's what the Hydrino guys have done. It's what we can do with Brouillon. I mean, these theories look the same. Or if you look at what's going on with the calculations that Forsley and Pines did, well, that's the same calculation as Jackson. It's the same calculation. They all do the same calculation. You just make slightly different approximations. And depending on the approximation, you get complete, I'll assume that the screening is angle dependent. I'll make this assumption. You make different assumptions and you get completely different results. And I think that I think that Pines's and Forsley's paper was less about the fact that the theory was correct and more about the fact that they were able to write down a theory which was coherent. And I think people were like, well, this is coherent and the calculations kind of make sense. So, okay, it's not completely bananas.
And that'll help a lot. But I actually think most physicists will be in denial about this until products are for sale. And I think that might be a couple years, because we have two companies that we know of that seem to have water heater designs that are likely to work, in my opinion, in the next couple years. So,
well, I've heard it's pretty amazing. We're hearing, Frank, you have an update from what's going on in Japan with Yoshino?
Well, they're developing a water boiling system, I think, for 1,000 watts. Presumably, it'll be demonstrated by the end of this year. So far, it's only, I don't know what's the wattage, but it's probably like less than 100 right now. So they want to up it by 10 times. They're one of the main investors is a Miura Boiler, which is the biggest boiling company in Japan. So it looks promising because their collaboration seems to keep expanding.
Oh, and just a heads up, Charles, regarding the BYU University of Utah situation. I left a link in the chat. At the patent office, we used to call this the, so, I mean, affectionately, we would call this the snitch hotline, right? If you feel really strongly about somebody else's patent application that you don't like, feel free to contact us here and submit your evidence. And so it's actually 35 USC 122E. would be the statute. So we can reject the case based on prior art that's presented by a third party against your application.
Yeah, I see. I didn't know about this patent stuff when when you study this in school.
Mm-hmm.
We knew that there was, I mean, the way we knew there was some controversy, and we knew that like Jones and Pons and Fleshman had a falling out. But I'm not a patent guy, so I didn't know that they had done this kind of stuff, and I didn't know about the Swedish patent. But that is outrageous. I just know that people tried to reproduce it, they couldn't reproduce it, and they're like, well, look, this stuff's very expensive. We can't afford to do this. That was basically the argument. We can't afford it. We don't have the money for this. And we have to, we have a job. We can't. It's. I mean, I think a lot of people. One of the arguments. I mean, I think it was by maybe your. Who was that, Frank? Who was the fellow who told us the argument about the blue LED?
What, Nakamura?
Was that it? Was just the comparing. I think people outside of science look at LENR like the blue LED. That people had tried for a very long time to make a blue LED.
That's right.
And there was a fellow who claimed he could do it, but he didn't really have the experimental protocol lined up. And it just took a very, very, very long time to figure out how to do it. For people to make it consistent. To turn it from just a single experiment that one person did to an engineering discipline where everyone can do it, or at least people who are very, very competent.
Yeah, that one, I think at the time nobody believed it was possible, and then I guess he snuck into the company during the weekends to carry out his own experiments, and then once they proved it, it was a phenomenal success. In Japan, it's considered controversial, right? Because I think as a more of a collectivist society, the inventor doesn't really get the full credit, right? And so he had to sue them to get, I don't know, just like 3% or some very small percentage of the actual profits from the invention.
Right. Yeah, that sounds about right. Well, look, the same thing with high temperature superconductivity. When high temperature superconductivity was invented, I think there were some guys in IBM Zurich, and they were just obsessed with these crystals that they use. They just were trying all sorts of experiments. They were just obsessed with it. And they just kept going in. They were convinced that they could do something with these Perscovites, and they discovered it. It was not like somebody said, "Okay, we're gonna build a high temperature superconductor." No, it was just people working by themselves, and certainly not with the sign off from IBM. They were just doing it. Now, I don't think it was
Right.
so I think this stuff is just much more. I mean, Larry's stuff is very interesting, right? Because it's really a high energy experiment. It's just basically, look, we're seeing enhanced fusion rates. I think people would believe that. There's still some I mean, I'll tell you though, if you talk to physicists I've talked to people about this who are, much better nuclear particle physicists than me, and that the first question they say is, well, screening is long range, fusion is short range. How does that work? And that's like, that was Munkhorst brought that up in the early papers. So I personally think that there's something else it has to be something else going on, at the short range effect. But that's not the same as having but that's a very, very complicated thing to flush out. And it's very difficult to really understand what's going on without doing extremely careful experiments to really flush out, is it this piece or that effect or this effect? That could take 50 years.
Right. There's another error I think we make when we let fusion scientists tell us whether something's possible or not. And we're talking about a money-making fusion reactor. They're not engineers, they're not economists. They don't actually know what stuff costs. And they really are on thin ice when they say we can't make money on something. Especially when we start to get in hybrid models with fission and fusion. But also, in the 1950s, all the attention on nuclear power of all sorts had to be a self-sustaining reaction, because the only thing that could be energetic enough to make a nuclear reaction happen was another nuclear reaction. But today we have transistors that can make megawatts and megavolts, and get them in concentrated places. We have lasers and all kinds of accelerators, just a whole lot of gear they didn't have in the 50s, and it's cheap. So claiming that there isn't economically easy ways to make nuclear reactions proceed, given the opportunities we have to build ignition systems today. In the 1950s, they had to build a campfire that would keep itself going. And today we can build something more like an internal combustion engine, where it goes out, 60 times a second, but we relight it each time with a spark plug. So that's kind of the goal for the cold fusion now, is see if we can't find a non-self-sustaining reaction that still makes money.
Well, look, I think that when I talk about fusion scientists, if I want to talk to a fusion scientist, I'm going to talk to the guy who's actually running a commercial fusion reactor project, not, some bureaucrat. And, if you talk to Monkhorst, you go, yeah, maybe this is possible. He was, you really see the difference between, that's why I bring it up, because, and not just because he's a friend of mine, but because, you're going to ask, is this possible? You're going to talk to, there's the climate change denier who claims this isn't possible. And then there's the guy who said, well, maybe it's possible. Let's go try. And let's see if we can make it work. And I think it's just a totally different personality type. And you're going to always have these people who just don't want to take any risks and want to deny things are possible. And, they're just so close-minded. And you have to go out and try things. Maybe Tri-Alpha, they can't. Tri-Alpha was, it kind of works, but it's very hard to control. It's not like, the Tri-Alpha, they put $500 million into what is basically a simple thesis calculation. It was not a sophisticated theory that they used to fund this thing. And this was, somebody could do the back, but it was not nearly as sophisticated as doing a complex ab initio calculation. It was just an idea. Oh, well, we'll try to build a reactor in reverse field configuration. Oh, okay. But it was, when the Tri-Alpha paper was published, I got to a little bit of almost an argument. Remember, Frank, who was that guy we were on the call with? The fusion guy?
Scott Sue.
Yeah, and the guy's telling me that the Tri-Alpha is a hot reactor. I'm like, I was in the room with Monkhorst and Rostocker when they got the review back on Tri-Alpha, and the reviewer was like, well, this thing's never going to work because it's not a high temperature reactor. It's not it's not like they didn't even want to do that because it was a completely different design than anyone had ever proposed. And I remember Monkhorst saying to me, these guys don't understand basic physics. The guys who are reviewing the paper, it's not the temperature, it's the fusion cross section that matters. But they have to change it, and they tell people, oh, it's a hot reactor, and then they'll accept it, right? They tell them it's a hot reactor, but they never. It was never, like I'm just saying from a political perspective, that's what they're telling them. Oh, it's a hot reactor, it worked, but no, it was never designed to be like that. It was completely the opposite. It was meant to be a completely different, innovative design. But if you tell people that's what you're doing, they will kick it down. So they changed the messaging. I think Larry has done a very good, and that's, I kind of had to bite my tongue on that because I was there. I remember very vividly that conversation with Monkhorst. And he was usually a pretty genteel guy. So he was really mad that they eventually got the paper published, the very famous paper on the Tri-Alpha design for their fusion reactor. But it was very much, I think here, this thing is just so different than what everybody is doing that it's just too far out. They can't absorb it. So, Larry has gone back and said, well, instead of starting at cold fusion or starting with muon catalyzed fusion, let's start with hot fusion. Let's do these beam experiments and prove that the beam experiments work. People will accept that. Once they accept that there's a screening effect in the metal, then over time, they'll begin to accept that the screening effect can happen in lower and lower temperature. And I think that's a very good strategy to try to get people to accept what's going on. You have to give it to them, in little bites. Well, I think we've lost everyone except, well, who else is left?
I think we're done. Yep.
Okay.
Thanks.
Sorry,
Well,
we have an engineering
Thank
meeting
you.
going on right now too. So
All right.
no
take
worries.
care.
All right. Thanks again, guys.
Thank you.
Thank you.
thank you very
Bye.
much.
Bye.
Bye.